To understand what is fatigue, let's consider this metal wire. What will you do to break this metal wire? Are you gonna pull it on both ends, or are you gonna bend it upward and downward repetitively? Well, I believe your answer probably will be to bend it repetitively, because based on experience, this method requires less effort compared to the first one. So this is a well-known example of fatigue failure. Fatigue is the catastrophic failure due to dynamic and fluctuating stresses. Here, dynamic and fluctuating stresses is the opposite of static stresses, which means the stress is constant. For dynamic and fluctuating stress, here's one example. The stress changes with time. To be more exact, this is a cyclic stress because it has cycles and it changes with time repetitively. So fatigue happens due to those kind of stresses. One example is the axle of this motor, which is connected to a weight. So due to the gravity effect of this mass, this axle will undergo fluctuating stress. When the mass is loaded or when the weight is loaded here, the stress will rise up. But when we unload it, it will be released. So it undergoes a fluctuating stress. Same in the case of this gear pair. The stress rises at the meeting point. So when the two teeth are meshing together, then the contact stress will be at its highest. But when the gear rotates, the stress will be lowered down, and it happens repetitively. Fatigue can happen in bridges, airplanes, machine components, and a lot of other situations. It is the single largest cause of failure in metals, and estimated to be involved in approximately 90% of all metallic failures. So that's why it's very important for us to understand and prevent fatigue failure. The characteristics of fatigue. First, it is due to long period of cyclic strain or stress. The term fatigue is used because this type of failure normally occurs after a lengthy period of repeated stress or strain cycling. And second, fatigue failure occurs at a stress level that is below the tensile or yield strength of the material. Unlike the failure happens at static load, the stress must be above the tensile and yield strength of the material for the material to break. But under the cyclic stress, the stress level doesn't need to be too high. When it's below tensile or yield strength, the fatigue failure can also happen. And the failure or the fatigue fracture is brittle-like, even in ductile metals, with little plastic deformation. And because it's brittle-like, so it occurs very suddenly and without warning. And also, it has the fracture surface that is very similar to the brittle fracture surface because it's brittle-like, right? Which is perpendicular to the direction of the applied tensile stress. Now let's take a look at the fluctuating stresses or cyclic stresses induced in the cross-sectional area of this wire when we bend it downwards and upwards. So now it's bending downwards, and we are going to observe the cross-section in the middle of the wire. So when it's bending down, the top portion of the cross-sectional area or the top portion of this wire is subjected in tension. So it's pulling, right? And the bottom segment or the bottom section is subjected in compression. So this is the stress on the top, which is in tension and is a maximum. And at the neutral point, the middle of this wire is 0. The stress is 0. That's the transition point. And after this 0 point, the stresses become compression and from smaller value to the maximum compression. So by convention, tension is positive and compression is negative. Now, when the wire is at equilibrium position, there is no stress induced in the cross section, so everything tends to 0. And when the wire is bending upwards like this, and everything will be reversed, which means the top will be in compression, pushing in together, and the bottom will be stretched out, which means it's in tension. So positive sigma on the bottom and negative sigma compression on the top. So if we trace the stress induced at a point, let's say this top point here, with time, and this is what we have. First, this point is subjected to tension and is a maximum tension. And then at the neutral position, it's 0. At the upward position, it becomes the compression and maximum compression. Of course, we're just showing the 3 distinct positions, but the change between each 2 positions are continuous changes. So that's why we connect those 3 points and it looks like this. And the same cycle repeats again and again. This is the fluctuating stress, changes with time, and which is the root cause of the fatigue failure. When such fluctuating load acts on the material, it will initiate something called microcrack. This crack will begin to grow with fluctuating load, and over time, it will cause an abrupt failure. Unlike failure due to static load, failure due to fatigue happens without any warning. It doesn't make necking as well, and the failure is unpredictable. In general, 3 different fluctuating stress time modes are possible. The first one is the reversed stress cycle. Second one is the repeated stress cycle. And the last one is random stress cycle. For the reversed stress cycle, the stress amplitudes are symmetrical about the 0 stress level, which means the maximum stress is a tensile stress and the minimum stress is a compressive stress, and they are of the equal magnitude. The second one, repeated stress cycle, the maximum and minimum stresses are asymmetrical relative to the 0 stress level. And the random one doesn't really have a pattern, it's just fluctuating. The magnitude and the direction of the stress changes randomly with time. Several parameters are used to characterize the stress cycle. They are mean stress, range of stress, stress amplitudes, and stress ratio. So the mean stress is the average of sigma max plus sigma minimum. And the symbol for mean stress is sigma m. So for reversed stress, clearly this mean stress is 0. Since sigma max is a tensile stress, sigma min is an compressive stress, and they are of the same magnitude. So that means when we use this equation, we need to use, well, negative for compressive stress and positive for tensile stress. Okay, and for repeated stress, then the mean stress is no longer zero because it's asymmetric about the zero axis or about the zero stress axis. So based on this equation, this is sigma mean, sigma m, the mean stress being visualized. The range of stress is the difference between the sigma max and the sigma mean. Again, we need to use negative value for the compressive stress. The stress amplitudes is the sigma r divided by 2. So this is the stress amplitudes for the reversed stress cycle and stress amplitude for the repeated stress cycle. And next one is the stress ratio, which is the ratio between the minimum stress and the maximum stress. So here again, keep in mind the minimum or the compressive stress is negative and the tensile stress is positive, which means for this reversed stress cycle, the R stress ratio will be a -1 because it's the positive sigma max over negative sigma mean, and they have the same magnitude. They are of the different directions, opposite directions. The fatigue properties of the materials can be determined from the laboratory tests. So this is a common test used to determine the fatigue properties of a material, and the specimen is mounted over here. We apply a cyclic load to the specimen. And also you can find a video of this fatigue test in Canvas. So this method sometimes is referred to as the stress life method, because if you measure at a given or specific level of loading, you measure the number of cycles this specimen can last before it breaks. So the number of cycles is the life of the specimen, and it expressed in terms of N. And then we change the load, we count the number of cycles it can last before it breaks again, and so forth, so on. After a series of tests, we can get the plot of stress versus life. But basically, during this test, the specimen is subjected to repeated stress, and it will count the cycles to failure. The alternating tension and compression stresses of equal magnitude are imposed, so that's why it's repeated stress. So it's completed reversed stress cycling with R equal to -1. There's one additional piece of information that you may need to do some calculations about the fatigue test we just mentioned. So for the rotating bending cantilever beam test, which is the test we just saw, the stress at any one point goes through a complete reversed cycle from maximum tensile stress to maximum compression stress, and they all of the opposite direction and the same magnitude. The maximum stress can be calculated using this expression, which equals to 16 times F. F is the load applied to the specimen. L is the distance between the bending force location and the supports. And D is the diameter of the specimen. And this is the maximum stress acting on the specimen. As we mentioned earlier, during the fatigue test, a series of tests is performed by subjecting the specimen to a different stress level and then record the number of cycles before the failure. So for example, at the beginning, we'll apply a very big stress, which is the ultimate stress or the tensile strength or tensile stress of the material. Therefore, it cannot last for the first cycle, right? It will break immediately. Therefore, the number of cycles is 0, so log n is 0 as well. So we plot the stress versus the logarithm of the number of cycles before failure, log n. Sometimes this stress is the maximum stress being applied to the specimen. Sometimes the stress amplitude is used on the plot. So it's stress amplitude versus log n. So just keep in mind to check the stress axis to clarify which stress number is used in the plot. And now we start to decrease the applied stress. As the stress decreases, we know the specimen will sustain more cycles before the failure. So we find another data point corresponds to the current applied stress, maximum stress or stress amplitude again, and we plot that data point against the logarithm of the number n, and so far so on. We continuously decrease the level, the stress level applied to the specimen and record the number of cycles the specimen can sustain and then plot the data. So for some materials, we figure out below certain stress level, the specimen will no longer fail. No matter how many times you apply this cyclic loads to the material, it will just last forever without breaking. So which means this n, number of cycles to break, is infinite, which will be a horizontal line on this plot. Right, log n, if the x value is infinite, now it will be a parallel line, a line that is parallel to the x-axis. So this stress level is called the fatigue limit of the material. So the fatigue limit is a limiting stress level below which fatigue failure will not occur. So it is the largest value of fluctuating stress that will not cause failure for essentially an infinite number of cycles. So which means if we use the material before or below the fatigue limit, it is safe. It will not fail because of fatigue. However, not all of the materials display this fatigue limit. There are two distinct types of fatigue behaviors. So you can see the top one and bottom one. The difference is the top one has a fatigue limit, has this horizontal portion in the SN curve, but the bottom one does not have a horizontal portion. So the top figure represents a material that displays a fatigue limit, and below this fatigue limit, no fatigue will happen. For some other materials, for example, the most non-ferrous alloys, including aluminum and copper, they do not have a fatigue limit. So the SN curve continues its downward trend at increasingly greater N values. So fatigue ultimately occurs regardless of the magnitude of the stress. And for these materials, instead of using the fatigue limit property, we have another property which is called the fatigue strength, which is defined as the stress level at which failure will occur for some specified number of cycles. For materials without fatigue limit, there are two important fatigue parameters can be obtained from the SN plot. The first one we just mentioned, which is the fatigue strength. is the stress level at which failure will occur for some specified number of cycles. So this is used when we design a component and we want this component to last for a certain number of cycles, for example, N1. And based on this number of cycles, we read off the plot, and the corresponding stress amplitude is the fatigue strength of the material at N1 cycles. That means when we use this component, we want it to last for those many cycles, then the applied stress should be below this fatigue strength of the material. Another parameter is the fatigue life, N sub F, which is the number of cycles to cause failure at a specified stress level, as taken from the SN plot. So this parameter is used when we know the loading status of the component. For example, we know the load be applied to this component is S1. And based on the load, we read the number of the corresponding cycles to failure, N, and we know after this many cycles, this component will fail. So based on this value, we want to replace the component before it reaches this number N. Fatigue failure happens in 3 stages. Stage 1 is the formation or initiation of micro crack due to cyclic plastic deformation. Stage 2, as shown in region B, progress to macro crack that repeatedly opens and closes, which will create bands called beach marks. The last stage, crack has propagated far enough that the remaining material is insufficient to carry the load and fails by simple brittle fracture, shown in region C. Cracks associated with fatigue failure almost always initiate on the surface of a component at some point of stress concentration, like shown in this example, is a steel drive shaft and crack initiation at stress concentration in the keyway. And after that, crack advances incrementally with each stress cycle, forming these beach marks, and finally, the brittle fracture happens at C region. There are many factors that can affect the fatigue life of the material. So here we're just going to present several of them. The first one is the stress amplitude S or sigma A. So when the stress amplitude decreases, the number of cycles for failure, which is N, will increase. So which is easy to understand, which means when we lower the stress level, the material will last longer, or the material will last for more cycles. The second factor is the mean stress. As the mean stress decreases, fatigue life increases. So the mean stress, if you still remember, is sigma m equals to sigma max plus sigma mean over 2, sum of the maximum stress and the minimum stress divided by 2. And the mean stress will change the location of the SN curve, actually will lower down the SN curve as the mean stress increases. So, for example, we have 3 mean stress values. Sigma 3 is the biggest and sigma 1 is the smallest. Now sigma 3 is corresponding to the line that is on the bottom, whereas sigma 1 corresponds to the SN curve on the top. So the bigger the mean stress, the lower the SN curve is positioned. Okay, then How about the fatigue life? Well, when we talk about the fatigue life, we mean we're talking about the number of cycles to failure at a given stress level. So we need to fix the stress level. Okay, so that means at a given stress level. Here, sigma, for example. Now the life or the cycles to failure is N3 for the mean stress of sigma 3, and N2 corresponds to a mean stress of sigma M2, and N1 corresponds to a mean stress of sigma 1. And since the n-axis increases to the right, then we know that N3 is smaller than N2 and smaller than N1. So which means when the mean stress decreases, the fatigue life increases. The last factor is the temperature. So as temperature increases, both fatigue life and fatigue limit decreases, which is due to the combination effect of the thermal fatigue. There are 3 general techniques to improve the fatigue life. First is to reduce the magnitude of mean stress. The second is surface treatment. And third is design changes. And we just mentioned the first one, which is decrease the mean stress will increase the fatigue life. So let's take a look at that one more time. So increasing the sigma mean stress increases in this direction. So this is the larger tensile mean stress, and moderate and near zero or compressive, which is the smallest sigma mean. And again, decreasing the mean stress will increase the fatigue life. For surface treatments, the idea is imposing compressive surface stresses increases surface hardness, which in turn suppresses surface cracks from growing. And the surface treatments including shot peening and case hardening, which can be done through carburizing. So for the first method, shot peening, the surface compressive stress due to plastic deformation of outer surface layer. And for case hardening, the surface compressive stress is due to carbon atoms diffusing into the outer surface layer, and both will put surface into compression. We should also use better designs to improve the fatigue life. So the basic idea is to remove stress concentrators when we design a component. For example, the sharp corners are the point of stress concentrations. So instead of using sharp corners, we should use rounding corners, which will reduce the stress concentration.